Good day, everyone. Just briefly, I come from University of Rijeka in Croatia, 2-hour drive from here, and Professor Petrović presented the topic, so I won't repeat that. So a true line of this presentation today is determination of fatigue behavior of metallic materials, specifically steels. So actually, how can we improve estimations of the behavior if we don't have enough experimental data? And how can we evaluate performance of some approximations that we make? So often in papers, we see that everybody obtains great results, and that's it. But maybe some more detailed evaluation is sometimes needed. So most of you are also familiar with challenges that come with performing experiments. You have to make series of decisions, but even if you do everything properly, cyclic experiments are long-lasting, they are expensive, and often data are not available in early stages of product design. So in the last 6 or 7 decades, estimation methods are being developed constantly. Mostly those are some kind of analytical expressions that try to predict estimate strain life parameters from monotonic parameters. Nowadays, more and more different kind of machine learning algorithms are used for the same problem. So what is basically the goal? To have better parameter estimation and more accurate determination of material behavior and time to crack initiation. What we do, we take monotonic properties from tensile tests. We develop either analytical equations. Maybe some of you are familiar with hardness method proposed by Rosler and Fatemi. Or nowadays, as I mentioned, we use machine learning model and obtain some estimations of strain life parameters. Then we can use that to calculate the strain life behavior. So it doesn't matter of the approach, but how we evaluate those methods. So usually we get some, we see some plots. We see, for example, comparison of experimental and estimated curve. And then in papers, we read, it shows good agreement, right? Okay, but we don't have numbers in particular, or we have just some, let's say, general trend data without details. Sometimes we see such scatter plots, and usually we have some kind of a trend line here. So scatter plot that shows agreement between experimental and estimated data, and we have some percentage how much data estimated fall within a certain scatter band. So that's usually a scatter band of 3. And then again, we say, okay, it shows good agreement. However, this is not enough to say, okay, our methods is really good, or maybe it's not that good. So Park and Song in 1995 proposed additional criteria. So let's say numerical criteria that also address not only the percentage of data that falls within a scatter band of 3, but also that try to estimate how well does the method estimate, like if we evaluate on a certain data set altogether or for a single material. And so those are these two. So you can imagine just one is connected to this trend line, this dashed one, and one is connected with single data sets, and then in a certain way it is calculated. They also proposed that an average value of these three criteria is calculated, and then to make some conclusions. So these criteria are more or less used. I would say less, but yet again, we have additional problems with evaluations. So those are commonly done on bulk material data, maybe disregarding certain subgroups of steels or metallic material in general. So everything is put together, I don't know, steels, aluminum, alloys. It's often performed for low cycle and high cycle fatigue regimes, and maybe some other specificities, particularities of certain material groups is disregarded. So high strength materials or low strength materials, this is a problem in general with all evaluations, and there is additional problem with machine learning based models. I will focus in this presentation on artificial neural networks because I did that. Because there are two aspects of evaluation. Usually performance of artificial neural network is made in some kind of way. So we use various statistics like mean relative error or coefficient of correlation, coefficient of determination, and then say, okay, this is good or this is not good. But the final result, so estimation of strain life behavior, is usually not done. Or if it is done, we also see some scatter plots, and we get a percentage of data that falls within the certain scatter band, and that's it, without these detailed criteria. But as far as I've seen, nobody used Park and Song's criteria for detailed assessment of results that are estimated with machine learning based predicted strain life parameters. Okay, so recently we published a paper in which we proposed that these Park and Song criteria are used, but that steels are divided results when we take those estimated strain life parameters and obtain some fatigue lives, that these are divided into low cycle and high cycle fatigue, and also that high strength and low strength materials are treated separately. You see the boundaries for steels. So my colleague will tomorrow present results for aluminum and titanium alloys that differ a bit according to division, but the principle is the same. And of course, we treat unalloyed, low alloy, and high alloy steels separately. Okay. Every time we do evaluations, we always use unseen data. That means those were not used for development of artificial neural networks, but we also wanted to get objective results. So we made sure as much as we could that also these data were not used in development of evaluation methods. So hardness method by Rosla and Patemi, uniform material law, and those that we chose. I will show you, because the time is limited, the results for strain life parameters first. But so yeah, every method takes monotonic properties, calculates in some way. We used artificial neural networks, and now we are in this step. We use the estimated values of strain life parameters. And in these diagrams, you don't have to focus on everything, because there's a lot of things that could be discussed, but maybe just mind these blue bars, because those results represent artificial neural networks. So what is presented here, percentage of values for each parameter that deviates up to 10, up to 20, and up to 30% from their experiment-based counterparts. So dark blue bars are for artificial neural networks, and The other colors are for analytical methods that I mentioned. So you see some much better results for certain groups of steels and for certain parameters. It could be discussed, but in this case, we will focus just on low alloy steels, where we observe better estimations. They are not like revolution, but they are better. Maybe these deviations up to 30%, we don't see that much of improvement, but in these deviations up to 10, up to 20%, we see some improvement, and we want to see how that affects on estimation of fatigue lives. Okay. So we use those parameters from artificial neural networks to calculate strain life behavior for 8 different total strain amplitudes. We could plot again these curves. I can present you one material, or I don't know, 5 materials, and say it's perfect, but I'm saying in advance it's not perfect. When compared to conventional estimation methods, for this material, yeah, it's really good, but we want to see in generalization of the method. Okay, so again, we are focused only on low alloy steels. We had 23 materials. Just to remember that we divided them into low strength, high strength steels. And when calculated, according to experimental calculated fatigue lives, they are divided into low cycle and high cycle fatigue regimes. Okay, and then we calculate Parkinson's criteria and obtain some numbers. The closer the number is to 1, that is the better. Yeah, but it's really difficult from such a table to conclude something. Especially if you are not really familiar with the criteria, but let's see just here. So in the first row, you have all data together, and in second to fifth, you have, so LS is low strength and low cycle fatigue, and that is the logic. And if we check the percentage of data that falls within scatter band of 3, it's not that bad. It's around 0.8, 0.9, so not so bad. But if we checked other criteria, for example, we see that we obtained minus. It can be minus. So for this EA total that considers that trend line when in scatter plot, if you remember that we saw, but I will present you on this slide. So here are diagrams, so for all data together, and again for that division that I showed you. And actually most of these points, as we see, the percentage fall within that scatter band of 3. Here we have some deviation, yeah, because this trend line is inclined. It's not really something we want. It's quite differs from the perfect line, let's say. And if we connect that with the table that we saw on the slide before, that is actually the group where we obtained minus for 1 criteria. And of course, if you have minus in 1 criteria and you want everything to be as close to +1 as it can be, it will affect also this average value of these 3 criteria. Okay, so what can we say? Are neural networks good? Estimated parameters or not? Neither good nor bad. But I just want to warn you that when we do evaluations, we have to be really careful what we will take and how we will use it. It's interesting also to see, so these low strength, high cycle fatigue results, what results we obtained with other methods, which are so analytical equations, which are widely used. So I just put a table for all steels together, so without that data division, and for that particular, let's say, problematic group, subgroup of data, and compare it to modified universal slopes method, uniform material law, and hardness method that performs really well. Here we can see, okay, artificial neural networks are either comparable to some widely used method, of course, for this data set we used, because estimations, evaluations always rely heavily on the data we have. And, you know, we must mind that we don't extrapolate and everything that goes with that. But when we see, when we check results for low strength, high cycle fatigue, and that criteria where we obtained minus, we see that also other methods don't perform that well. It's better than artificial neural networks, definitely, but also 0.3, 0.4. And when we see this average value, artificial neural networks are again somewhere comparable with UML, slightly worse than modified universal slopes method and hardness method. But it's interesting to see that, so this is calculated for all data together, so with parameters that are obtained from the trend line for all materials. But this says how well does the method estimate particular data set. And we can see that artificial neural networks that we developed actually estimate rather well. It's not rather well, but it's better than the other methods, so significantly better. But this average value is let's say comparable. Okay, so what was, I had also frames. What is the point of this presentation? The point is that methodology for evaluation of these methods, it doesn't matter which tool you will use, has to be the same. So it has to be unified, so you can compare the results to some other paper. It is always the problem also with artificial neural networks that you usually cannot repeat somebody else's research, and you usually don't have their codes results, so you can make direct comparison to your investigation. So that is actually the conclusion, that comparability is a must, because for now we can only trust that we can judge that something looks reasonable enough, and we have to trust the results based on those scatter diagrams, on maybe comparison of experimental and estimated curves. We are also always interested in outlook and how we can improve estimations, and for now we were experimenting with estimations of parameters all together, not separately as was done. I didn't go into details because of the limited time. So we think there is something can be improved if we did estimations for all parameters together. That's it. This is our funding, and thank you for your attention.